So good morning student. Today we will discuss change in gene frequency in the presence of selection. So in previous lectures we have discussed the change in gene frequency which is occurring due to the systematic processes. And there are three systematic processes. One is your migration, second one is your mutation, and third one is selection. We have covered migration and mutation in previous lectures. So today we will discuss how the change of gene frequency occurs in a population when selection is made. So first of all, we will define what is the selection. So it is defined as differential reproduction rate, that is the number of progenies left by individual to reach maturity or equilibrium. Right? Now, the proportional contribution of offspring to the next generation is called the fitness of the individual, or it is also called as adaptive value, and you may call it also as selection value. So these are very important when we study the selection. So we will take the first example of selection when selection is made against recessive and there is a complete dominance. So how various relationships or how the change in gene frequency occurs generation after generation when we made the selection against recessive and complete dominance is there. Let us suppose that we have two genes A1 and A2. A1 with their initial frequency say P0 and Q0, and A1 being completely dominant to A2. I mean to say A1 is completely dominant to A2. So now let us suppose the coefficient of selection against A2 is S. This is the selection value, fitness value, or adaptive value. So if we multiply the initial frequency, that is P0 and Q0, by the fitness value of each genotype, we obtained the proportionate contribution of each genotype to the gamete that will form in the next generation. So I am just considering the two allele A1 and A2. So the possible genotype we will get, say A1 A1, A1 A2, and A2 A2. A1 A1 is homozygous dominant, where A1 A2 is heterozygous and A2 A2 is homozygous recessive. And their initial frequencies, since P0 is the frequency of A1, so it is P square 2PQ, P0 Q0, and for A2 it is Q0 square. And if we sum all these frequencies, say P0 square plus 2P0 Q0 plus Q0 square, so it is equal to 1. And if we consider the selection values for these genotype like this 1, 1 and 1 minus s. Why this 1 minus s? Because we are selecting against the recessive. So I use 1 minus s for A2 genotype. Now this sum is not equal. If I multiply the initial frequency with these selection values, we will get proportionate contribution of each genotype to the gametes that will form in the next generation. So I just multiply these frequency. So after selection, gametic contribution, when I multiply 1 with P0 square, I will get P0 square 2P0 Q0 1 minus S Q0 square. And if I take the sum of these, this sum is not equal to 1 because of the selection. So what will be the sum? This sum can be find out just by putting say P0 square plus 2P0 Q0 plus 1 minus S Q0 square. So if I simplify it, so it becomes P0 square plus 2P0 Q0 plus Q0 square minus S Q0 square. Now this thing is equal to 1 as I have already said. So ultimately I will get 1 minus SQ0 square, the total of all the contribution of A1, 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 A2 and A2, A2. So you will get 1 minus SQ0 as the total contribution. Now we have seen that total gametic contribution is not unity because there has been a proportionate loss of say SQ0 due to selection because the sum is 1 minus SQ0 square. So due to selection this loss has been occurred. That's why the total contribution is not equal to 1. Now we want to find out the frequency of A2 genes in the progeny in next generation. We have gametic contribution of A2 individual. How we will find out the gametic contribution of A2 individual in next generation? That can be done by the contribution of A2 individual plus half of the contribution of heterozygotes and divide it by say 2. That's why I am using half plus half of this. So you can find out the gametic contribution of A2 individual. The new gene frequency is say Q1 because in initial generation it is Q0. So after one generation of selection, I denote it by Q1. This can be done Q0 square 1 minus S. This is the gametic contribution after selection plus half of the frequency of heterozygotes. So it is P0 Q0. And if I simplify it, so Q0 square minus SQ0 square plus I am substituting 1 minus Q0 in place of P0. So it is 1 minus Q0 into Q0 divided by the total gametic contribution in next generation, that is 1 minus S. This is Q0, not Q2. So if I further simplify it, what I will get? Q0 square minus SQ0 square. Q0 is multiplied with 1, so it is Q0. Q0 is multiplied with Q0, so it is minus Q0 square divided by this is 1 minus SQ0 square. This is 0. So now this cancelled out. And what we left? I left only Q0 minus half of Q0 square minus SQ0 square divided by 1 minus SQ0 square. So this is the frequency of say A2 after one generation of selection. Right. So now we are interested in to find out the change in gene frequency. What change occurs after one generation of selection? Suppose this change is represented by delta Q, which is occurred or which is resulted from one generation of selection. So this delta Q is nothing. In generation 1, the frequency of A2 is Q1, and in initial generation, the frequency was Q0. So the change in gene frequency will be equal to Q1 minus Q0. And if I substitute the value of Q1 and Q0 in these relations, so I will get Q0 minus SQ0 square upon 1 minus SQ0 from this. This is the value of Q1 minus Q0. Now simplify it. If I simplify it, I will get 1 minus SQ0 square as denominator, and this Q0 is multiplied by the denominator. I will get Q0 plus Q0 cube, and I think it is SQ0 cube. SQ0 cube. So Q0 minus SQ0 square and 1, this is Q0 plus Q0 cube. So on simplification, what I take, this minus SQ0 square, if I take common, this is again wrong here. It is Q0. So this Q0 cancelled with this. We have left with, I just do it by hand. So from this relation, what I get if I take the LCM 1 minus SQ0 square. So this is Q0 minus SQ0 square minus Q times, you can say 1 minus SQ0 square. So on simplification, I will get Q0 minus SQ0 square minus again Q0 and plus SQ0 cube divided by 1 minus SQ0 square. Now this cancelled out. When this cancelled out, I left only with, if SQ0 is taken common, say minus SQ0 if I take common, so what I get, 1 minus Q0 divided by 1 minus SQ0 square. So delta Q will be equal to minus SQ0 square minus SQ0 square 1 minus Q0 divided by 1 minus SQ0 square. So here we have to note certain points. If the coefficient of selection against recessive is say small, means if S is very small, then what happen? So if the coefficient of selection against recessive is small, the change in gene frequency will a slow process. Then the quantity SQ0 square will be so small that the denominator for practical purposes, because the change in gene frequency delta Q we have taken as minus SQ0 square into 1 minus Q0 over 1 minus SQ0 square. When the S is very small, very nearly equal to say 0, so this term will be vanishes, and for practical purposes we will always use delta Q as minus SQ0 square 1 minus Q0. So I will use this expression for change because this S is very small. We have taken SQ0, we will take this denominator as unity. So delta Q for all practical purposes will be used by this relation. So now delta Q will be maximum when? When Q0 is say nearly equal to 2 by 3, then your delta Q will be maximum. So only in that case the method gives good response to the selection. And another point you should keep in mind that selection is most effective at intermediate frequencies and become least effective when your Q0 is either large or small. So if the value of Q0 is lying in middle, say zero point 0.4 to zero point 0.7, then the selection is effective. So selection is most effective at intermediate frequency and become less effective when Q0 is either large or small. Now selection for or against recessive gene is extremely ineffective when your recessive allele is rare. If the frequency of Q is very small, means this A2 gene is very rare, then if we perform the selection against this gene, so it is ineffective. So keep these things in mind when selection is made against recessive and there is a complete dominance. So now we are interested in to find out the amount of change in Q over number of generations. Now we have developed this relation. We know that the delta Q is equal to SQ square 1 minus Q0 square. Q0. For all practical purposes, I will use this change. Now, if this delta Q can be written as, say, dq by dt, differential equation, where t denotes the time as measured in units of generation. So, this equation can be written in the form of differential equation by replacing delta q by dq by dt, where t denotes the uh, time as measured in unit of generation. So if I write this thing like this, say dq upon dt in place of delta q, and here minus is there, I am forgotten. So this will be equal to minus sq 0 square over 1 minus q0. Can I write like that? So dq by dt can be written as s. I am ignoring the subscript because I integrate this over the initial generation to nth generation. That's why I am just using this q instead of using q0. So we will get this relation. Now from this, if I separate the terms containing q on one side and rest on other side. So what I will get, dq divide by q square 1 minus q will be minus s into dt. Can I write like that? So this can be written as like this. Now if I integrate both sides, so what I will get? And the limit of integration, since q is the frequency of A2, and this frequency is changes from q0 to qn, and t is my time, it is from 0 to n. So I integrate both sides, say dq upon q square 1 minus q between the range, say q0 to qn, and in this side I integrate between the range 0 to n s dt. So if I integrate both sides, we have q0 to qn dq upon q square 1 minus q is equal to minus 0 to n s dt. Now, this integration is very simple because s is constant, I can take it out and it is t. So, when I integrate this part, so there are two methods to integrate this equation. First method, in which I will use a result, that is dx upon x square ax plus b and its integration is 1 by bx plus a by b square log of ax plus b over x. This is the result I will use. So if you compare, right, now if you compare these terms with this thing, so what I will get? Here ax plus b. So I will get a is equal to say -1 because this q is my x. I am taking x as q. So the coefficient of q is -1. So a is -1. And this b is +1. B is +1. And your x is q. So this thing, so it becomes say x square. This is my b minus ax. So or a is -1, b is 1, and x is your q. So I can apply direct this result to this integration. So if I apply this result, so I will get -1 over bx minus 1 over x is q, b is 1. So it is 1 by q. Then a upon b square. A is my -1. B square is 1 ka square means 1. So it is -1 by 1. Log of a is -1. So minus a. This is not x. I think this is q. In place of this is q. So minus q plus 1. B is 1 and x is q. In the range of q0 to qn. And on right hand side, what is the integration of dt? It is t in the range 0 to n. When, and s is there, when n is when t is n, it is s it is n, and when t is 0, it is 0. So it is Sn. So you will get 1 upon q, this one, -1, 1. So it is minus is there. Log of +1 minus q. So 1 minus q over q in the range q0 to qn. And on right hand side, I will get minus Sn. Now simplification. You will get, if I substitute first qn, so I will get -1 by qn minus log 1 minus qn divided by qn and minus q0. So this is q0. Actually, this is q0 plus log of 1 minus q0 over q0. Here both, because minus minus becomes both plus, so Sn minus Sn. Right? So we will continue it. So in last slide, we have find that minus qn log of 1 minus qn, this is 0, not qn. This is 0. So we will get these expressions. And if I simplify this, how I can simplify it? This is q0 is my plus. So I write like that 1 upon q0 minus 1 upon qn. I am using these two terms. And these two terms contains log. So plus log of 1 minus q0 upon q0, divide it by log of 1 minus qn upon qn. I will get this. And when I simplify it, this part only, so I will get log of 1 minus q0 upon q0, and this is qn upon 1 minus qn. So ultimately I will get log of Qn into 1 minus Q0 over Q0 into 1 minus Qn. So if I simplify this, you will get Qn 1 minus Q0, Q0 1 minus Qn is equal to minus Sn. And if I further simplify this part, so this becomes Qn minus Q0 over Qn Q0. So I just use Qn minus Q0, Qn Q0 plus the remaining things. And now from here, you can find out the value of n. So the value of n can be found out 1 by s. I just take the minus common. When I take minus common from both sides, if I take minus common from these two terms, so Q0 minus Qn divided by Qn Q0. And when I take minus common, so the numerator and denominator interchanged. That's why I put plus here. So the number of generation required I can find out with the help of this expression. So this is my first method. So these are the relation I have find up to now. Now in second method, what we do is we just uh, take say the integration between q0 to qn of dq upon q square into 1 minus q is equal to minus integration 0 to n into s dt. So in second method, I will use I will use 1 upon say q square 1 minus q as say 1 upon q square plus 1 upon q into 1 minus q, and on simplification I will get 1 upon q square plus 1 by q plus 1 over 1 minus q. So if you simplify it, you will get this expression. So the integration from q0 to qn is equal to dq q square upon 1 minus q can be written as 1 upon q square plus 1 by q plus 1 upon 1 minus q dq minus Sn. So their integration is very simple. 1 upon x square is minus 1 upon x. So it is minus 1 upon q plus log q 1 upon q, and its integration is log q. 1 upon 1 minus q is integration is minus log of 1 minus q between the range q0 to qn, and right hand side will be minus Sn. So after simplification, all these simplification I have already mentioned, you will get log of qn upon 1 minus qn minus log of q0 upon 1 minus q0 minus 1 upon qn plus 1 upon q0 is equal to minus Sn. And your Sn becomes log of q0 upon 1 minus q0 minus log of qn upon 1 minus qn plus 1 by qn minus 1 by q0. So if I simplify it, ultimately I will get the expression as we get in previous method. So n is equal to 1 by s log of q0 1 minus qn upon qn 1 minus q0 plus q0 minus qn upon q0 qn. Now we will consider certain special case. When selection against recessive is there and when S is equal to 1, what does it mean? There is a complete selection against recessive. and the recessives are eliminated because the selection value A2 I have 1 minus S. When S is equal to 1, so complete selection against recessive is there. This frequency becomes 0 and your Q will be eliminated from the population. And under such condition, your Q1 will be equal to minus SQ0 plus Q0 upon 1 minus SQ0. If I put S is equal to say 1, so what I will get? Q1 is equal to minus Q0 square plus Q0, 1 minus Q0 square. And if I take Q0 common from upper side, you will get 1 minus Q0, and now this cancelled out. So I will get Q1 is equal to Q0 upon 1 plus Q0. Similarly, in second generation, Q2 can be obtained on similar way, Q1 divided by 1 plus Q1. And if I substitute the value of Q1 here, which is Q0 upon 1 plus Q0, so I just substitute the value of Q1, I will get this expression. And if I simplify it, I will get Q0 upon 1 plus Q0, and this becomes, if I simplify the denominator part, what I get? I will get the LCM as 1 plus Q0. So it is 1 plus Q0 plus Q0. So it becomes 1 plus 2Q0 upon 1 plus Q0. So I just change the numerator and denominator 1 plus Q0. Now this 1 plus Q0 can be cancelled out. So we will get say Q0 upon 1 plus 2Q0. If I keep going on this side, I can find out Qn as Q0 upon 1 plus n Q0. So this is the expression. And from here, if you just cross multiply, or if you cross multiply this expression, means 1 plus n Q0 is equal to Q0 upon Qn. So I will get this expression. And now nq0 can be written if I transpose 1 to this side. So nq0 will be equal to q0 upon qn minus 1. And nq0, if I simplify it, these are n, not these are n. If I take LCM, so it is qn, q0 minus qn. So you will get this. And we can find out the value of n. N is nothing but n can be find out q0 minus qn divided by this q0 qn. So we can find the number of generation required to change the gene frequency from q0 to qn. When n tends to infinity, means number of generation is very large, then your qn will approaches to 0. If we do a complete selection against recessive for large number of generation in complete dominance, then this gene Q can be completely eliminated. Thank you.